Resume recording. All right, everybody. What are we? We're 11:01, and it is the 23rd of March, and we've got a couple of things to do. So here's where I'm headed. Unfortunately, not to the coffee store, but we headed back to ozone, and I'm going to do a quick 2-minute recap of where we've gone, maybe 3 minutes, and then we will keep on with the ozone story because we're not quite done yet with stratospheric ozone. Then the plan is to put that aside and start on the material in chapter 6, which is climate change. And because of Snowvid and the fact that I'm about a lecture behind, what I'm going to do is I will introduce you to the greenhouse effect and see how we go from there. But certainly I will have to spread climate change across exam 2 and exam 3. So next Tuesday is exam number 2, right? March 30th. And I will talk a little bit about that on Thursday. So I'm going to leave some time in class on Thursday to talk about exam 2. I won't do a full review in the sense because it's the same type of questioning, but I do want to spend a little bit of time going over the review that I've put out and sent you all. So hold off until Thursday for that. And then I will also make myself available over the weekend. Under these circumstances, I'm happy to do that. And so if you need to meet with me, I know the calendar is already filling up, but if the calendar fills up to the point that I can't meet you, then we'll have to carve out some time over the weekend. And if that's okay by you, that is fine by me. Okay, so let's get going. The quick review here, right, is, let me start with this slide. I've just pulled a couple more slides back in here. One, remember, there are 2 different types of ozone, right? There's the low-level tropospheric ozone, human-made, and it's a pollutant. It's a constituent of chemical smog. Then there's the second type of ozone, which occurs in the stratosphere. It is not human-made, right? It is created and destroyed naturally by sunlight, and is by far the most important account of ozone. One, because it's 90% or more of the ozone in the atmosphere is in the stratosphere, but 2, is not a pollutant. It's actually beneficial and it absorbs ultraviolet radiation, right? So that was the first big sort of set of points that I made. The second one was this cycle. This is how ozone is formed and destroyed naturally, right? Sunlight splits diatomic oxygen, O2, in the stratosphere, individual oxygen atoms. One of those oxygen atoms combines with an O2 to form an O3. And as sunlight strikes that O3, it absorbs that UV radiation, so that protects us from UV radiation. But in so doing, it breaks down the ozone into oxygens and O2s. And so there is this continual natural formation and destruction of ozone that goes on. Right? So that's point number 1. I hope everybody's reasonably happy and comfortable with that. Okay. So the second part then is the chlorine cycle. Right? And the chlorine cycle, and as I sort of alluded to on Thursday, everyone, the chlorine cycle is a challenge because there's 2 components to it, right? There is the destruction of ozone by chlorine, okay, which is certainly part of the story. Then the much bigger part of the story, which we haven't gotten to yet, is why is the destruction of ozone so significant over the polar regions, right? Ozone is destroyed in the tropics, that's true, but it's at a much lower level and far less significant than occurs over the poles, and especially Antarctica, right? So this is the second story that we looked at, and let me just quickly summarize what we covered here. Remember that we put out chlorofluorocarbons and other ozone depleting substances, but we focused on chlorofluorocarbons. Sunlight breaks those down. It frees up the chlorine, right? The majority of that chlorine that is freed from the CFC ends up here in these so-called reservoir gases. Chlorine will join with hydrogen to form hydrogen chloride. Chlorine will also form with nitrogen and oxygens to form this chlorine nitrate. These 2 are the most important reservoir gases. They don't destroy ozone, but they store the chlorine for the destruction of ozone later. And those reservoir gases are the ones that over longer time periods are transported to the poles by the atmospheric transport. as an average, that's how the winds work. They get the heat out of the tropics and they transport these substances to the poles. The chlorine cycle can kick in at this stage, right? Some of this chlorine is freed and can destroy an ozone, right? So it steals an oxygen. It becomes this chlorine monoxide. Another oxygen steals that one and frees up the chlorine. So at this early stage, at this early stage, no, you're good, Keegan. At this early stage, the breakdown of the CFC and the freeing up of the chlorine starts destroying ozone, but it's at an extremely low background level because most of that chlorine ends up in these reservoir gases and gets transported to the poles, right? Any questions? Any issues? All good? Okay, all right. Then there was this summary which basically shows the discovery of the so-called hole in the ozone layer, right? So in the early 1970s, Rowland and Molina show unequivocally that chlorine in CFCs is destroying ozone. And by 1984, a group of authors show that it's not just destroying ozone, but it's destroying ozone catastrophically over the South Pole, over Antarctica, right? So this shows the average minimum ozone over the South Pole, where you see this decline in stratospheric ozone, right? And a continual decline reaching very low values in the early 1990s. And that has continued with a couple of ups and downs along the way. So let me stop there and just make sure that everybody's on the same page, because what we're going to do now, if I just go back one, let me see if I can go back one. What I'm going to do now is I'm going to explore what happens to these reservoir gases, the hydrogen chloride and the chlorine nitrate, as they're transported to the poles. Right. Questions? Everybody happy with that?
We have a question.
Okay, Chanera, let's fire you and then the next one in.
So the average minimum ozone, it's just explaining the size throughout time, but that's all we have to know about it.
Yeah, so it's the average thinness or lack of thickness of ozone as a concentration. And anything thinner than 220 Dobson units is considered severely depleted ozone. And just showing the trend over time that we continued to deplete ozone throughout the 1980s, 1990s. And even though it continues to be thin, we seem to have arrested that continual destruction. Does that make sense, Chanera?
Yes, it does. Thank you.
Okay, awesome. Any other questions?
Yes. So what transports the reservoir gases from the tropics to the polar? Yeah.
Okay, so that's a great question, Desai. It's a key question, right? So what transports it are the atmospheric winds, right? The tropics are warm and humid, right? The poles are cold. Why? Because the sunlight is more direct for longer periods of time over the tropics, right? The Earth is angled at 23.5 degrees north and south. In other words, the sun stays overhead between 23.5 degrees north and south as it travels around as the Earth travels around the sun in a year, right? But there are times of year when you get above the Arctic Circle where the sun disappears for months at a time. So the poles are cold and the tropics are hot. So what happens? Well, the tropics send out all of that energy, and we're going to get to that next when we talk about climate change. But the tropics send out all of that energy in the form of winds and ocean currents. And the poles go, you know what, Josiah, I'm too chilly. I'm going to send you some cold air and some cold ocean currents. So there is this continual circulation between the tropics and the poles, and that's how the atmosphere gets these gases down towards the poles. Does that make sense?
Yes, thank you.
All right, good question. Okay, cool. So let's move on. Now we start here. So what are we looking at here? Now we're going to get to the key question. And let me be really clear. I'm going to ask this in the exam, right? I am going to ask you unequivocally to explain to me how and why ozone is destroyed so rapidly over the South Pole, okay? So it's an intricate and complicated story, but I'm gonna break it down into some constituent parts, right? So what are we looking at here? So what we're looking at here is an image over Antarctica, right? So here's Antarctica here. You can see that, Australia down here, okay? South America over here. And there's that pretty cool country down here on the southern tip of Africa. And what we're looking at are a series of little black circles that are going along the Greenwich meridian, the 0-degree line of longitude, okay? And these are simulated weather balloons showing the path of a weather balloon over 24-hour periods. In other words, this one that I'm circling here goes from here all the way around to there in 24 hours, and 24 hours later it's there, and 24 hours later it's there, and 24 hours later it's there, right? That's a 4-day trajectory of that balloon. And the colors show ozone. Anything in blue is the ozone hole. So why am I showing this? And it's beginning to expand a little bit on Josiah's question. What do you notice about the trajectories of those weather balloons distributed along that line of longitude? What do you notice? They're doing what?
I mean, they're going around in a circle, but
Yeah.
I mean, they're getting like the closer you are to the middle, the more it's going to stick to the middle, I suppose.
Uh-huh. So that's exactly right, Gavin. So they're going around in circles. They're rotating, right? These weather balloons are going around in these eddies, right? They're circulating around the pole like that. Does that make sense? And that's exactly what happens over the South Pole and the North Pole, right? Now, I know some of you, maybe all of you, have heard of the polar vortex. Everybody heard of the polar vortex, right? Snowbird. Polar vortex. So what's the polar vortex? The polar vortex is this big blob of cold air that sits over the North Pole and it sits over the South Pole. And it spins around, right? It rotates because the Earth is rotating. So this blue blob that you see here of thinner ozone and the trajectories of the air balloons give this impression of a rotating blob of air. And that is exactly what happens over the South Pole, okay? This rotating blob of cold air. So what happens over the South Pole is this. On and around the 23rd of March, okay, now we're at the South Pole here, right? So at about the 23rd of March, which is, well, hey presto, that's today.
Today.
That's cool. So around about today, if you're at the South Pole, something is going to disappear. The sun's going to disappear, right? And the sun's going to go down below the horizon on the 23rd of March. And then as you get into April, by the time you get to May, there's no sun. I don't know if anybody's seen the movie March of the Penguins. If you haven't, it's awesome, right? About those poor penguins all clustered in the South Pole, protecting their eggs. The sun goes down, okay? The sun disappears. And what happens to this blob of cold air? It gets colder and colder and colder. The vortex becomes this much bigger blob of cold air, and it gets extremely cold over the South Pole as the sun disappears. What happens today, fortuitously, if you're sitting on the North Pole? What comes above the horizon?
The sun.
Hello, here comes the sun, right? It pops up, and as you go into April, May, and June, by the time you get to June and you're sitting on the North Pole, you've got 24 hours of sunlight. I cannot wait to go to northern Sweden one day and play golf under the midnight sun, where the sun doesn't set, right? Everybody with me? So when you look at this next diagram, this is what this explains. It shows the yearly sun graph on the South Pole, right? And if this confuses you, don't panic. All I'm trying to show here is that when you get to, here's March, and March the 23rd is right in here, we've got, as the sun begins to go down, and I've tried to draw this on the right-hand side, when the sun goes below the horizon, you get what is known as civil twilight, and then it goes a little bit lower, you get this nautical twilight, it gets a little darker, and eventually it becomes night, all right? Straight out night. So here we are in the early part of April, all the way through to the end of July, you are in total darkness over the South Pole. Does that make sense? Right? No sunlight. The air gets incredibly cold. And you're probably thinking, so what? Why is that important, right? Well, why that is important is these things begin to develop. The things you see in the sky here, right? And these things are an incredibly unusual type of cloud, okay? And they're called a PSC. Oh, that's a rather exuberant C. A PSC, a polar stratospheric cloud, all right? They are clouds that form in very, very dry air. They're made up of tiny, tiny ice crystals, okay? They also are made up of nitric acid, and I'll explain why in just a second. They're not the type of clouds that we see outside, right? They cannot generate rain or anything like that. They occur at very high altitudes. This is in the stratosphere, everybody. So we're up at about 15 to 20 miles. And they can only form when temperatures go below minus 78 degrees Celsius. That's the key. When temperatures get that low, these clouds begin to form, right? And it is on these clouds that the chemical reactions take place that set the atmosphere up for the destruction of ozone, okay? So the sun has to disappear. The vortex has to get deeper and stronger and get colder. And then you have to get these clouds to form because, and I repeat, it's on these clouds that the chemical reactions take place. Everybody with me? Cool, thumbs up, all right? Now, here's another way. I thought, how do I show this, right? Here's another way to show the importance of the temperature. So what you're looking at here is temperature in degrees Celsius on this axis over here. And I've got Antarctic winter on the bottom axis here. So that's South Pole winter, right? So South Pole winter, March the 23rd, today the sun goes down. By May, we're in the South Pole winter. By the middle of July, those penguins are freezing, right? South Pole winter. The North Pole winter starts in November, December, January, when it is our winter. Does that make sense? Okay. And what I want to show you here are the averages, right? The average temperature. The solid line is the average temperature over the Antarctic, and this is the average temperature over the Arctic during the respective winter periods. Okay. All of this shaded area shows you the total range of the data. And this horizontal line here that I've drawn is the magical minus 78 degrees Fahrenheit line. What do you see? This is a complicated diagram, but if you can appreciate this diagram, you're almost there. What do you notice about air temperatures?
The Antarctic air temperatures are well below negative 78 degrees Celsius. So to me, like when you said like the clouds that form at negative 78 degrees Celsius, it seems like prime like environment for them to form.
Prime polar stratospheric cloud environment. Yeah, Holly, you've just discovered a new phrase. I like it. It's exactly right, right? Because here's minus 78. And once you get to May, look at this. Between May and September, even into early October, stratospheric temperatures are below that threshold, right? In other words, stratospheric clouds can form underneath that curve, right? As opposed to the North Pole, where it's much warmer. See that? There's just this little bit where the temperatures go below there, right? And also, the Northern Hemisphere temperatures are much more variable. Does everybody see that? The blue shading is much narrower. All right, now, excellent, Holly. Okay, now for a free cup of coffee at Summer Moon, Professor Fulbright. Why? Why is the South Pole so much colder than the North Pole, or anybody?
Is it because the sun isn't there?
No. Good effort, but no. The sun is below the horizon over the Southern Hemisphere winter, and it's below the horizon over the Northern Hemisphere winter. So atmospherically, the situation is the same.
Is it because of the clouds and what they're made of, and that's why it traps all that?
No, but I like your reasoning. I see where you're headed, but no, the clouds functionally and their chemical makeup are the same, Gavin, in both hemispheres.
Because of the warm ocean currents surrounding Antarctica.
Ooh, keep going.
The air currents. I got nothing.
Okay, you're in the ballpark. I'm seeing air currents. Polar vortex is bigger in the south from Ari. It is bigger. The polar vortex is bigger. It's deeper, but why?
Is it because the Arctic has more water around it, so more air currents go across it to make it colder?
Who's just a cup of coffee? I don't see you. Who was that?
It was Ashley.
Ashley. Say that again.
It's because Arctic has more water around it, and then the ocean has a lot of fast currents, so it makes the land colder.
Exactly. Nicely done, right? The South Pole is a continent, this big, gigantic continent, right? Bigger than the United States in the lower 48. And what's it covered with? It's covered with ice and snow. So the air that sits above that icebound continent gets incredibly cold and takes on the characteristics of the air sitting above it, right? In the Arctic, what's the Arctic? The Arctic isn't a continent, it's ocean. Yeah, it's nippy for sure, okay? And there's oceanic ice over the Arctic, but there is much more water in the Arctic, and therefore the polar vortex is much warmer, right? Water warms up much more slowly and cools down much more slowly than land does. You folks know that, right? When you look at Wichita, Kansas and San Francisco, for example, believe it or not, San Francisco and Wichita, Kansas are on the same line of latitude, right? They actually have the same annual average temperature of 66 degrees Fahrenheit. But I bet you if you lived in San Francisco, your closet would look completely different than you lived in Wichita, Kansas, right? Because of your proximity to water and the moderating effect of water. Does that make sense to everybody? Okay, Ashley, awesome. Janira, you got a question?
Yes. Can you repeat that one more time? You said the
Yeah, you
South
bet.
Pole is a continent, which means it's covered in ice and snow. And you said the air above the South Pole mimics the air in the atmosphere? Like,
Yeah,
what did you
exactly.
say?
So
Okay.
exactly. So you've got this big continent covered with ice, right? And the sun goes down and the air is swirling around over that continent. Okay. So that air gets colder and colder and colder and colder as it sits above that continent, right? The air sitting over the Arctic, yeah, there's some sea ice there, but there's also ocean there. So the air is much warmer over the Arctic than it is over the South. You got it.
Yes, thank you.
Okay, perfect. So the South Pole is much more conducive to polar stratospheric clouds because of the land-water differences that you find there. Okay, so let's see if this works. Is that animating? It should be spinning.
It's spinning.
It's spinning. All right, love it. So watch as this goes. I'm going to let it run a couple of times. Just watch the dates. The colors here are the thinning or the opening up of the ozone hole. July, right? July, ozone's good. Sun begins to come up. Sun begins to come up. Sun's above the horizon. Hello, sun. Goodbye, ozone. Right? Look how quickly that ozone hole opens up over the South Pole. Everybody see that? Things are normal. I hope you can see the spinning polar vortex. And then the sun's up. And as the sun comes up, the ozone gets depleted and disappears. Okay? That's the thing that completely baffled scientists, right? Once those guys had said, look, we know that CF chlorine's destroying ozone and everything, they couldn't solve why ozone was depleted over the South Pole so rapidly at certain times of the year. So here's the answer, okay? All right, everybody needs to have another coffee and load up for this little diagram. This is the diagram that explains it. And this is the one I want you to be able to at least articulate and at least be able to explain. This explains how the ozone over the South Pole depletes so rapidly when it does, okay? Now, I know we've got a complicated bunch of little blobs along the top here. This is the legend. So let me just explain what's going on with this legend. I've just singled these out. Here's a hydrogen atom, a chlorine atom, nitrogen, and oxygen, right? When two chlorines join together, right, that's molecular chlorine. This one here is HNO3, that's nitric acid. This here is HCl, hydrogen chloride. Ooh, I remember hydrogen chloride. This one here is chlorine nitrate. These two here are the reservoir gases that we talked about earlier that Josiah have now been transported down to the South Pole, okay? So there's the legend, just for your reference. And here's a part of a polar stratospheric cloud. So let me put this in motion, and I'm going to click through it slowly. So here's what's happened. We've emitted CFCs into the atmosphere. The CFCs are broken down, right? We've talked about that. Some of the chlorine goes and destroys ozone very minimally. Most of it gets tied up in hydrogen chloride and chlorine nitrate, the reservoir gases. and those gases are transported to the poles and swirl around in the vortex, okay? So they're swirling around in the vortex, and that's occurring in January, February, March. They're happy, nothing going on, okay? The sun goes down, the temperature gets cold, the temperature goes below -78, and the polar stratospheric clouds form, okay? That's step number one, right? Step number one is the pole, and just focus on step one on the left-hand side here. Step number one is the polar stratospheric cloud forms when the sun disappears and the temperature drops below -78 degrees Celsius, okay? Step number one. The reservoir gases that have been transported to the pole and are just sitting there, the hydrogen chloride and the chlorine nitrate, they hop onto the cloud, right? They go onto that cloud. Those clouds are critical for the reactions to take place. No clouds, no reactions, okay? So the hydrogen chloride hop onto the cloud and they react with each other, okay? So this is step number two. The hydrogen chloride and the chlorine nitrate react with each other. The two chlorines get together, right? So these two chlorines get together and they form molecular chlorine, Cl2. Everybody with me? What's left behind? The hydrogen, H, and the NO3. And HNO3 that is left behind is what? Nitric acid. Everybody see that? That's the nitric acid. So the sun goes down, the clouds form. The reservoir gases that have been transported to the poles go, there's my base. I can see the cloud, I hop onto the cloud, I react, I form the molecular chlorine and the nitric acid, okay? Then what happens? All this is all happening in the dark while the penguins are freezing underneath. Then what happens is the molecular chlorine, right? The Cl2, the molecular chlorine hops off the cloud. So step number three, the molecular chlorine down here hops off the cloud, right? See that? Cl2 hops off the cloud and the nitric acid stays on the cloud. That's why when I showed the picture of the cloud, I said they're made of nitric acid. That's the nitric acid comes from. So the ice crystals are there. Now it's got a bit of nitric acid with it and they stay on the cloud, okay? There's still no destruction of ozone because Cl2 here cannot destroy ozone. This is all happening in the dark. But then what happens in step four is the sun comes up. And the sun comes up gently at first above the horizon and then quickly above the horizon. And what does the sun do? The sun splits apart the Cl2 into chlorines and off it goes. That chlorine attacks an ozone molecule. And that's the runaway catalytic reaction. And the ozone depletes incredibly rapidly until the chlorines run out of gas, they run out of fuel. So I need to stop there and make sure everybody's happy with that. And I'm happy to go through it quickly again if you need.
Can you repeat step 4, please?
Yeah, so step 4, I'm glad you asked that, Janira. Step 4 is the critical step here, right? Because all of these reactions, and let me just reiterate, I probably didn't say this. Let me just put the annotator on here for a second. So step 1, step 2, and step 3, all of these are referred to as dark reactions. They are all occurring in the dark. When the sun's down, the clouds are formed, and all of that stuff is reacting on the cloud. Step 4 is started when the sun comes up above the horizon towards the end of July and early August, peaks above the horizon, and the UV rays from the sun split the two chlorines, the molecular chlorines, into free chlorine. And then the chlorine cycle starts. The chlorine attacks an ozone. It rips off one of the oxygens to form a chlorine monoxide. It then attacks another oxygen. The oxygen steals the oxygen and frees up the chlorine. So now that's exactly what we showed at the beginning, that's the chlorine cycle, right? But over the tropics, there's very little chlorine that's freed up at that stage. That's why most of the chlorine ends up in these reservoir gases, gets to the pole, hops on the cloud, And that buildup of all that chlorine on the clouds is why you've got this huge reservoir sitting there until the sun comes up and splits. I think that's a little story. Okay, so that's the reason why ozone depletes so rapidly over the South Pole, right? And here's the, whoops, I'm going backwards, sorry. Here is the key diagram that shows that. So what are we looking at here, right? This diagram, and I've just updated this. These are all available on the web. This shows the depletion of ozone, the minimum amount of ozone across the year for the South Pole. The black line here, the solid black line that you see here, so I'm just going to highlight that curve. That solid black line is the 1979 to 2020 average. The blue curve is last year, 2020, right? And all the shaded stuff, all of this stuff just captures all of the data. So that's all of the data in the dark grays and 90% of the data and 80% of the data. You don't have to worry about that. And I've included here this year up until last week. I think I downloaded this on Friday, right? So look what happens here. Let me see if I can change colors here. Let's do this ugly longhorn UT orange. Whoa. Okay, so look what happens here, everybody. At this time of year, not much is going on, right? Ozone is at about 250, 240, 250. It's a little depleted. No big deal, no big deal. Now the vortex forms, gets colder. The polar stratospheric clouds form, it's colder, right? Everything's happening on the clouds, the dark reactions, everything's happening on the clouds. And then what happens at the end of July? The sun comes up. Bingo. Step 4 in the cycle kicks in. And just look how rapidly ozone depletes from the end of July to early August when the sun comes up to that last week in September when ozone reaches a minimum. That's what the scientists couldn't explain. Over a 2-month period, ozone is just decimated over the South Pole, right? Everybody see that? And then the cycles run out, right? The clouds evaporate, the nitric acid disappears. You don't have to worry about that part of the cycle. And the system, the catalytic reactions basically stop, right? So when you look at this one, so you've seen this before, right? Take a look at this. This shows, this is the same one you saw before. It shows ozone over the South Pole. It drops down to 1994. 2019 was an interesting year. Okay, look at 2019. Ozone goes back up to 161. Those are levels that they hadn't seen in 25 years, right? And everyone was like, oh, cool. The ozone hole's recovering, okay? And if you look at this, if I just try and put this another color on here, if you go from 1994, it looks like this is in fact going up, right? It looks like ozone's recovering. 2019 was a really fascinating year. The polar vortex started developing and then it collapsed, it disappeared, right? The stratosphere over Antarctica warmed up, and it warmed up because of something called El Nino. We don't have time to talk about that. We can examine that later. But the stratosphere over the poles got much warmer than it otherwise should have. But now look at 2020. 2020 looks ugly, right? 2020's ozone minimum is the lowest we've ever recorded. Now that doesn't mean to say that the ozone hole is opening up and now getting worse and worse and worse. We've got a high year and an unusually bad year, and an unusually bad year because in 2020, along with COVID, the stratosphere was really cold over the South Pole, and they had unusually more polar stratospheric cloud. Another way to express this, remember, is the size of the ozone hole. So here's the size of the ozone hole. On average, you can see the size of the ozone hole has been around the size of North America. Last year, it was much smaller, 2019. Here's 2020. Not so good, right? So that gives you the longer term picture. I like this diagram because it shows the 2020 hole, just how extensive it was, right? And you can see why. I don't know whether it was Uchenera maybe, or someone asked about, why is it a hole? Why do we call it a hole? Is it a hole? Something like that. I mean, it looks like a hole, right? But it's this significantly depleted core of ozone, right? And if you're struggling for a sense of scale, this is this is the 2020 plot, right? So I go back to the 2020 plot here. 2020, right? It was really low here in 2020, okay? And there is the size of North America, and there's the size of Antarctica. So, you know, the story with ozone is mixed. Why is it mixed, and what are we doing about it? Well, one of the things that has been really critical in the ozone story is this global agreement that came out in 1987, right? I'll explain this diagram and then we'll wrap up ozone here. So in 1987, the world's governments got together and said, all right, we need to do something. Remember, in 1974, they had shown that CFCs were destroying ozone. By 1984, they had shown, 1984-85, they had shown that the ozone hole was really bad over the South Pole. Governments got together and said, we need to phase out and ban CFCs, right? And that was what the Montreal Protocol was. It was this global agreement to reduce and eventually phase out and ban CFCs. And so what does this diagram show? So this diagram shows the two most important reservoir gases, hydrogen chloride and chlorine nitrate, right? The two most important reservoir gases. The blue diamonds here are essentially the red circles and the green triangles added together. And here it's written as CLY. We refer to that as free chlorine, but the total sum of chlorine available to do the destruction. So this is 1985. You can see chlorine's going up, chlorine's going up. Chlorine in the stratosphere reaches a peak here in 1995, right? About 8 years after the Montreal Protocol is enforced. And it goes through various ramifications and modifications. And it looks like we are now potentially headed downwards, where hopefully by 2050 or so, the ozone hole will begin to recover because we are seeing a gradual reduction of chlorine in the stratosphere. Folks, it doesn't mean to say that we're not going to get a year where you get a dramatically thinner amount of ozone or a bigger hole like we've just had in 2020. We're going to get those fluctuations. What we're looking for is the trends in ozone, and it looks like the ozone story will be hopefully an environmental success story. So let me stop there, everybody, and see if there are any questions or comments. And then I'm going to just introduce you to some basics on climate change and before we launch into that in more detail. So thoughts, comments, questions?
Okay, so I read about this in the news the other day. How they were saying how like by 2100 we could have like 6 months of summer, and I was wondering like how is that going to impact the ozone?
Sorry, say that again. You chopped out there. You read that we were going to have 6 months
of summer by like 2100.
I'm not sure. Where did you read that?
It was like a couple days ago. I think I saw it on like NBC or something.
I wonder what they meant by 6 months of summer. They're just talking about warmer summer temperatures because the seasons are caused by the axial tilt of the Earth. So we're not changing that.
I think they meant like warmer temperatures for longer periods of time.
Okay, I see what you're saying. So warmer temperatures. So not astronomically 6 months of summer, but we're going to have what seems like longer periods under a warmer world, under climate.
Yeah. Drier areas as well.
So that's but in the article they were just discussing that in terms of temperature, not in terms of stratospheric ozone, right? Is that right to know? Ozone wasn't part of that article, or was it?
I don't think so, but I was just wondering how that
so
would
it's an interesting question, right? We're going to explore that when we look at climate change, on what these potential changes in climate were. And the problem is, if you just take that at face value, so if we're going to have temperature-wise, thermally extended summers and longer summers and warmer summers, some may say, okay, well, that's going to be good for the ozone, right? Because that'll mean warmer South Pole, and therefore we won't have the polar vortex, and therefore we won't have the stratospheric clouds. That's not necessarily true, right? We don't know how long-term trends in temperature are going to play out in terms of extremes, right? So we're still going to get winter. There's no doubt about it, because that sun is still going to go below the South Pole. It's just a question of how that plays out. Good question. Question from Caitlin. What did the protocol ban? It banned the use of chlorine and CFCs, right? So it banned CFCs and other ozone depleting substances. Yeah, thanks, Madeline. Any other comments or questions? All right. I don't know why I don't learn. I always set one lecture aside for ozone, and it always takes me 2. So maybe when I'm 70 years old, I'll learn to set 2 aside. All right. So here's where we're going to next. What do we have? We have 10 minutes. So that's great. That gives me a little bit of time for fun. All right. Okay, we're going to move on to chapter 6. Okay, and chapter 6 deals with this 800-pound gorilla in the room called climate change. I cannot tell you how often I get this question, right? I'm sitting at Starbucks or at Summer Moon, as it will be, Holly, to keep you happy. But I sit at Starbucks and I often get this question, right? Let's strike up a conversation. Someone will say, what do you do? They'll see the TCU sticker on my laptop. I'll say, I teach at TCU. Oh, what do you teach? Oh, environmental science. Oh, so do you believe in this global warming thing? Or is this just some big hoax, right? I get that question all the time. So let me make some general comments before we start this three sessions to this topic, right? One of the things I will do, and I hope I'm careful about this, is I'm going to tell you what the science tells us. Okay, we're going to follow the data and follow the science here when it comes to climate change, right? So we're going to talk about the greenhouse effect for sure, and that's the first part. And we will probably just get to that on Thursday. That'll be the first part. It is fundamentally important. I've always believed this, to understand the greenhouse effect and understand how the atmosphere interacts with gases, both natural gases and human-made gases. Because right here, the data can be skewed, right? And we can go off track. So we're going to talk about the greenhouse effect. I have to talk about the media, the politics, and bias, right? I'm going to try and be as objective as I can, but I'll give you the kind of takeaway version now. No environmental, perhaps no scientific issue has been so misappropriated by special interest groups than the topic of climate change and global warming. That's just a fact. And that's especially true in the United States, right? So I'm going to be very open and transparent and say, this is what the data tells us. This is what we're seeing in the media, right? I'm also going to say, this is my opinion, and you are more than welcome to disagree with me. Your grade does not depend on my opinion whatsoever, right? But climate change and global warming, and I'll make a quick distinction between the two in a second, right? That doesn't operate in a vacuum. That operates within a media and a scientific communication environment that has become massively polluted. No pun intended. We're going to talk about the evidence, right? We're going to see what evidence there is to suggest that the climate is changing. We're going to go to the science, right? I'm going to look specifically at carbon and temperature and tie that back to the greenhouse effect. And then we're going to scratch our head and say, what now, right? Given what we've talked about in the lectures. So it's a complicated topic, and I think rightly or wrongly, climate change and global warming is the one environmental issue that kind of perhaps oversees them all at the moment. To some people, it's seen as an existential threat and the greatest environmental catastrophe that we potentially face. To others, it's seen as a hoax dreamed up by the Chinese to hurt the American economy, right? Somewhere in between there is the truth. Somewhere in between those 2 points is something that we need to, I think, be able to talk honestly and openly and scientifically about. Incidentally, everybody, climate change and global warming, we use those in my world with very specific meaning, right? Climate change refers to a range of impacts by a changing climate getting warmer and colder, and both of those. So climate change just isn't warming, it's cooling of temperatures. It also involves changing patterns of precipitation, and what changing patterns of precipitation mean for ecosystem responses and so on. Global warming is used specifically to refer to the anthropogenic acceleration of temperatures. Humans putting out gases that are causing the planet to warm, right? So there are 2 things. They're related for sure, but climate change and global warming we use very specifically. I think nowadays some people like to use climate change instead of global warming because they feel like global warming is too political. And if you use global warming, you're either being pro-Trump or anti-Trump or pro-Biden or anti-Biden or pro-Al Gore or anti-Al Gore. The reality is that global warming in the scientific world is used to describe an acceleration of global temperatures as a result of the emission of gases by human activity. Climate change is a much broader issue. So I hope that maybe clarifies things a little bit. Does that make sense to everybody? Okay, any thoughts or comments before we keep going? Questions? All right. Well, what do we got? We've got 3 minutes. So I'm going to stop right there. On Thursday, we're going to talk about the greenhouse effect. That'll take about 30 minutes. And then I'll take 20 minutes to review for exam number 2. And then the 2 final lectures of climate change will be the media and the evidence. And that'll be the science and carbon. So that's the lecture for today. Have a great day, everybody.
Thank you, you too.
Thank you.
Thank you.
Thank you.
Thank you so much.